Okay, welcome in everybody. Cruise into this morning's session with a bit of math specific skill development. So if you want to get involved in a bit of that, then feel free to study along. Here we go.
Okay, so let's jump in. So we'll start with scientific notation. Now, really, what I like to think of scientific notation as is just a different way to represent numbers. So if we had 4, for example, we could represent that as 4, and that's completely fine. But it might be, in certain situations, for whatever reason, better to represent this as 2 times 2. I don't know what those situations are, but this is more just to kind of set the foundation for what scientific notation is. So it's just a different way to represent the number. You could also represent this as 2 times 2 times 1 if you really wanted. Now, what we're doing in scientific notation is just figuring out a way to represent numbers, but what we're doing is representing it in how many times we need to multiply by 10. So for example, if we had 100, we would want to represent this as 10 times 10. And just like how we did in this example here, we want to put times 1. So the reason why we do this is the form that we want to get in scientific notation is a single digit number out the front, times 10. So this is, if you kind of just follow along, we have two groups of 10 here, right? Because 10 times 10 is 100, and anything times 1 is just itself. So this is still just 100. But the reason we've done this is to give us that single digit. So what we then do is we put a 2 up here on the tens to represent how many groups of 10 we have in our number. And really it's as simple as that. So if we had something like a 1000, this would just become 10 times 10 times 10 times 1. So therefore this 1 would come out the front, and then we'd have 10 to the 3 because we've got 1, 2, 3 tens, and that's why we've got 10 to the 3. Now I mentioned that this is a really convenient technique. So what I'm doing at the moment doesn't really seem very convenient because we have to expand these numbers into how many times we have to multiply by 10. So if you had, a million, all of a sudden you can see that number's going to be quite large. It's going to be really hard to actually do these things. But you can take a little bit of a shortcut. So if we just have, let's say 1, okay? Every time we multiply that by 10, what happens? So if we times that by 10, this just becomes 10. Now, if we multiply this number by 10, I'll do it down here, it then becomes 100. And if I multiply it by 10 again, it's going to become 1000. So you see that every time I multiply by 10, all I'm doing is just adding a 0. That's the only effect of what I'm actually multiplying by 10 by, and that's just what 10 does. You just add a 0 on the end. So what we can actually do, instead of having to break numbers up manually into these powers of 10, what we can do is we can kind of write this number down. So let's say we do 10,000 now. So we're getting a little bit larger. We just write the number down, and you just want to put a decimal point. A lot of numbers won't have a decimal point in them. We don't really write 10,000.0, but we just put that decimal point at the end of the number, and we just jump that 1, 2, 3, 4. We jump it, and what we've essentially done is just count how many zeros are in that number. Now, by counting the number of zeros in that number, we've now counted how many times we've multiplied that number by 10. 1, 2, 3, 4. So that means that whatever's left to the left-hand side of that decimal point comes out the front. So 1, times 10, and then however many jumps you've done, that becomes the number on top of the 10, so 10 to the 4. Something that I'd just like to say now, which will become relevant later, is that we can actually stop this jumping process wherever we want. So if I take that 10,000 again, put the decimal point in, I'll do a different color this time. We can jump as many times as we want, as long as we just stay consistent to this rule. So let's say I just jump 1, 2, 3 times now. So 1, 2, 3. Decimal point goes here. So whatever's to the left comes out the front. And then however many times I've jumped is the number that goes on the 10. So everything's exactly the same. Now, as I'm just kind of signposting this because this will become relevant later. But remember, with scientific notation, all we're doing is representing the same number a different way. So this number is exactly the same as this number. We've just kind of transferred one of the, if we highlight the differences, we've got a 4 versus a 3 here and a 1 versus a 10. So as I said, the effect of multiplying by 10 is just adding a 0. So we've kind of taken one of these 10s from here, because we've got one less, and we've just kind of multiplied it onto this 1, which has then given us that 10. So it's the exact same number, just represented a different way. And as I said, this will be very useful later on. Okay, so moving on. I've used numbers like 1,000, 10,000, things like that. But this works for other numbers as well. So if you had, let's say, 200, you just do exactly the same thing. So we just go 1, 2, whatever's left on the left, 2 comes out the front, times 10 to the 2. Easy as that. Not particularly relevant for the GAMSAT, but you can have weird looking numbers. So you could have something like 3,794, something like that. And we just need to know how to handle those as well. So it's exactly the same. We just put a decimal point in, 1, 2, and wherever we stop, that's just the number that it becomes. So if we stop there, it'll be that. But usually the convention is to go all the way to the start. Now, basically, you just read that number. So as if that's a 3.794. That's exactly what just comes out the front. So it's 3.794 times 10 to the 3, because we've done 1, 2, 3 jumps. So it's the exact same process, but we just end up with this number with decimals in it. And the reason for that is that this is essentially just to demonstrate this again. It's 3.794, oops, times 10 times 10 times 10, right? Because we've got 10 to the 3. So what happens if we do this once? If we do this first step, that's going to become 37.94. If we do it again, it'll become 379.4. And if we do it one last time, we get 3,794, which is our original number. So just to show you again that we're just representing numbers in a different way. Now I mentioned that this is not particularly relevant, and that's because usually in the GAMSAT, if I got a number like that, I would just round that to 4,000. Okay, so I'll talk more about this as we go through this maths course, but I really want to introduce early that the main thing that we care about in these calculations, and I'll show you some examples later, isn't really the exact finite accuracy. The main thing is getting the tens right. And what I mean by getting the tens right is this number here. So this 10 to the 3 is the most important thing. If this is 3.794 versus this one, which will just become 4 times 10 to the 3, this difference here in the 4 compared to 3.794, that's not going to make a difference. The reason is because a lot of the answer options are things like 10, 100, 1,000, 10,000. Look through some of the practice material and you'll see this. So how on earth can anyone get confused between B and C? It's because they make mistakes in their calculations involving the tens. Okay, so having 4 versus 3.79, that's not going to get you from B to C. But if you all of a sudden said that this was 4 times 10 to the 2, all of a sudden, now our numbers are a factor of 10 different. And that's exactly how different these answers are, okay? So that's the most important thing. We'll keep touching on this again and again and again, but get comfortable with making the maths easier, but keeping the main kind of thing, which is usually the number of 10s in that equation. Okay, now also just need to touch on small numbers. So if you had something like 0.0001, this thing applies exactly the same way. So in anything, it's actually easier because we already have our decimal point in the number. So we just do the same thing. So 1, 2, 3. Now a lot of people make this mistake, but they stop here because they now have that number. You just need to remember that whatever, if let's say we did stop there, remember what I said, that whatever's left, wherever that decimal point stops, that's what we're left with. So here we would actually be left with 0.1. Now that's okay. If we wanted to, we could represent this as 0.1 times 10. Now, just do this now, so don't worry too much about this minus sign. I'll explain that in a second. But you can see that I've done 3 jumps, so that number is a 3, okay? That's perfectly fine. But generally, what you would do is you would jump 1, 2, 3, and you'd go to the right-hand side of this number so that you're left with like a positive single-digit number. So in that case, we've done 4 jumps, so you get 1 times 10 to the minus 4, okay? So again, these numbers are equivalent, but you would generally go to the right-hand side of that number so you don't end up with a decimal for your scientific notation. Now, as I alluded to, we've got one slight difference here, and that's negative. We've got a negative number in there. It's not 4, because that's the number of jumps that we've done. It's negative 4. Now, people have all kinds of funky ways to remember, if it's negative or positive. I like to just keep it simple. So you've either got a big number, or you've got a small number. And by small, like you can tell that this number, that's a very small number. So if it's a small number, it's a negative power. If it's a big number, it's a positive power. And I just kind of do a fact check. So for example, with this one, I've done 4 jumps. So my answers are either 1 times 10 to the negative 4 like I've got here, or 1 times 10 to the positive 4. And I would just look at both of these options and say, okay, I've got a small number, so I'm going to pick the one with the negative power. And I just kind of do this little sanity check in my head. And as I'm learning anyway, you'll get, naturally, you just know if it's a negative or a positive, but just as you're starting out, I would just do that fact check rather than try to complicate it with all these rules about if I jump to the left, it's blah, blah, blah. It gets a bit too confusing for me. Also thought it's worth mentioning that even though that power is negative, this isn't a negative number, okay? This is a small number, but you could also have a negative small number. So you could have negative or a negative large number. So you could have negative 30,000, right? This would be the same thing. So 1, 2, 3, 4. 3 times 10 to the 4, but this would be negative 10 to the 4, negative 3 times 10 to the 4. And you could also have negative 0.01, and this would be 1, 2. So it's become 1 times 10 to the negative 2, because we've gone, it's a small number, so it's negative power. But then this negative comes out the front. So if the number's positive or negative, that's completely separate to the positive or negative on the exponent, which is this number on top of the 10, completely separate to that. And lastly, we may need to also go from scientific notation back to kind of normal numbers. Now, this is very much the same. So we could have 2 times 10 to the 5, and we need to then write that as a number. So I just do exactly the same thing. I put my 2 down with a decimal point, and I just jump. So I just do 1, 2, I might actually do some different color. So I go 1, 2, 3, 4, 5. Put my decimal point there, and all of these jumps, because remember, just like how we've done with all the other examples, when there's a 0, we jump over the 0. So what we've now done is we've done the jumps, and then we just fill in the zeros. So that would be my answer, 200,000. And just as we're learning, just do both directions, because we don't know if it's going to be large, or we kind of do, but you could jump to the left or the right. So how do you know which way? I personally would just do both. So then we go 1, 2, 3, 4, 5. Then I'd fill in these numbers. So basically we've got 0.00002, or we've got 200,000. And I would just again do that sanity check. What's the exponent? Is it positive or negative? Positive, large number. I'm picking 200,000. That's really easy as that. Now in the GAMSAT, I think every number should be represented in scientific notation. And the reason is because then we can apply our index laws. So I kind of touched on this a bit before, but the number at the top of the 10, that's called our exponent. And the bottom, the actual 10, is called the base. Now, there are a bunch of different index laws, but I just wanted to touch on these 4, okay, to start with at least. So you can expand this as you go, but these are the ones that you just need to have down pat. Now, what they say is that if I'm multiplying 2 numbers with the same base, so that's all this A means, it's just that the base is the same, because A is the same as A, then we can just add together their exponents and kind of drop one of those bases. So, for example, if we had 10 to the 3 times 10 to the 2, these have the same base, so therefore we can just add the exponents. And I find it quite easy to associate adding with this multiplying, because when you multiply numbers, they get bigger anyway. Multiplying, as I touched on earlier in the other video, is really just a glorified adding. So this will become 10 to the 5. We just add together those exponents. Now, by the same token, if we are dividing those, we can just minus the exponents. And again, that comes back to what I talked about in the first video of dividing just being kind of glorified subtraction. And just some other ones is that anything to the power of 0 just equals 1, and anything to the power of 1 just equals itself. Okay, so those are kind of the 4 basic, really simple ones that I think we need to understand. Now, why I find these so useful is that we can solve quite intimidating sums really, really quickly using this technique. Now, I think most people would look at this and freak out, or they'd have to do all of them like individually, and it'd take a while, and what do you do when you multiply by a decimal, and all these, it just feels scary. However, when we do scientific notation and couple that with our index laws, it all of a sudden becomes very, very easy. So what does that look like? Well, we just convert all these numbers to scientific notation. So 1,000 is just 1, 2, 3. Now, I'm not going to do all of these, but that would just become 1 times 10 to the 3. Okay, so I'm not going to explain each of them. this step by step. I will do all of them, but I might just speed through a little bit. So that's what the first one becomes. Now, anything times 1 is just itself. So usually when we have this, we actually just knock that 1 off. But I'm going to leave it here for a reason that will become clear later. Okay, so then we times that by 1 times 10 to the negative. How much it is? 1, 2, 3, 4. Negative 4 times 1 by 10 to the 2 divided by 1 times 10 to the negative 2 times 1 by 10 to the 4 times 1 by 10 to the 5. This is always my first step. So I've got a little mnemonic for this, and it's called SOS. So you can put that into the frame. So first step, scientific notation. Second step, organize. And then last step is solve. Okay, so this could be an ABBA song or a Rihanna song. I know both of them. They're very good. So SOS, that's your mnemonic. And I honestly do this with pretty much every calculation I need to do in the GAMSAT. Now, what I mean by organize is I move all the numbers to one side and all of the powers, by powers I mean these tens with an exponent on them, move them to the other side. The reason for this is that, as you'll see in a second, I've picked numbers that are just, 1,000, 10,000 again. So we just have 1 out the front here. But as I'm sure you can acknowledge, in the GAMSAT, it's very unlikely that you're going to get all these nice round numbers. You're probably going to get some other numbers in there. So this will become more relevant later, but basically it's just a way to prevent mistakes. And a lot of my maths is just about coming up with processes that prevent mistakes. So what this organized step would look like is 1 times 1 times 1 times 10 to the 3 times 10 to the minus 4 times 10 to the 2. Divided by 1 times 1 times 1 times 10 to the minus 2 times 10 to the 4 by 10 to the 5. So you can see how I've just moved all the numbers to one side, all the powers to the other, but it's exactly the same as above. And this is because 3 times 2 is the same as 2 times 3. When you're multiplying things, it doesn't matter what order they're in. One can be over there, one can be over there, and then you can swap them. Doesn't really matter. So this will still equal the same thing. And this will become helpful later. So we organize and then we solve. So I do all of the numbers, and then separately I do all of the powers. So this will just become 1 over 1, right? Because it's all just ones there. Times by, now we just apply, as you can see, all of these powers, it's going to get confusing, use a different color. all these powers have the same base. So that means we can apply index laws. And really, every time we do scientific notation, by definition, scientific notation is just representing numbers in terms of a base 10. So we're always going to get 10, and that's why it's so useful, because it means we can just always apply these index laws. So what that means is, because we've got the same base, we can just add together these exponents. Now, I like to just kind of add all the positive ones first. I find that easier mentally. So I just do 3 plus 2, which will equal 5, and then plus minus 4. Now, a plus and a minus will equal a minus, okay? So if I'm adding negative 4, that's like subtracting 4. So it's like 5 minus 4, which gives me 1. And then on the denominator, I'll do the same thing. So it'll be 5 plus 4, so that's 9, minus 2. So 9 minus 2 is 7. So 10 to the 7. And then this solve set can sometimes go into two phases. So the final answer will be 1 times. Now again, we have the same base. So now, but in this case, we're dividing. Now it's very important that you get the order right with these things. So we need to remember it's the top minus the bottom. So this will actually become 1 minus 7. Now this will get hard if you have a negative number in here, because this will be 1 minus 7, which becomes 1 plus 7. So just be very careful when you're dealing with a negative. Well, actually, just be careful when you're dividing them, because the order is important. So this will just be 1 minus 7. This will become 10 to the power of negative 6. So hopefully through that you can appreciate that we've gone from something that looked quite intimidating to something, to an answer relatively quickly. And with a bit of practice, you can really get very, very efficient at this process. Now, as I mentioned, it's not particularly relevant to just have all these round numbers. So let's just rub these out and put in some harder numbers. And with a bit of practice, you can really get to the power of negative 6. So hopefully through that you can appreciate that we've now, because this will be 1 minus 7, which becomes 1 plus 7. So 5 plus 4, so that's 9, minus 7. And then this solve set can sometimes go into two phases. So the final answer will be 1 times. Now again, we have the same base. So now, but in this case, we're dividing. Now it's very important that you get the order right with these things. So we need to remember it's the top minus the bottom. So this will actually become 1 minus 7. Now this will get hard if you have a negative number in here, because this will be 1 minus 7, which becomes 1 plus 7. So just be very careful when you're dealing with with a negative. Well, actually, just be careful when you're dividing them because the order is important. So this would just be 1 minus 7. This will become 10 to the power of negative 6. So hopefully through that you can appreciate that we've gone from something that looked quite intimidating to something, well, to an answer relatively quickly. And with a bit of practice, you can really get very, very efficient at this process. Now, as I mentioned, it's not particularly relevant to just have all these round numbers. So let's just rub these out and put in some harder numbers to deal with. And I'll show you that really the process just stays exactly the same. So the number of jumps is going to remain the same. So the only thing that's going to change are these numbers here. So this will become 8 times 10 to the 3, 4 times 10 to the negative 4, 9 by 10 to the 2, 3, 6, and 5. And then that just means when we organise, and you can kind of see now why the organised step is useful, because if we were doing all these numbers, we'd have to do the 3 over here, then go over here to the 2, then come back to that. And in my head, that just looks really messy. And I've made the mistake before where I just kind of I just don't see one of these numbers somehow. And you just don't really recognise how easy it is to make these mistakes until you have this huge calculation that you need to do. So I find just by organising it, I'm far less likely to make one of those mistakes where I leave a number out. And again, that's the kind of mistake which is going to significantly change your answer. If you leave out an 8, that's basically the same as leaving out a 10. So just make sure that you're doing everything you can to not make one of these mistakes. So that's what the organised steps here. So we get 8 times 4 times 9, 3 times 6 times 5 in the denominator. So how I like to do this is just make the maths easy. So this is what I was talking about before. It's not going to matter if we change one of these numbers a little bit. It's not going to get us from, 100. To 1,000 or something like that, which is usually how far the answers are apart. So if I'm looking at this, so my golden rule is make the maths easy. And by easy, I mean, if I ask you that question, you will immediately know the answer. So without even thinking, you just know the answer. So 2 times 2, 4, that's it. How I like to do these. 3, 6, and 5. Two, 3, 6, and 5. And then that just means when we organise, and you can kind of see now why the organised step is useful, because if we were doing all these numbers, we'd have to do the 3 over here, then go over here to the 2, then come back to that. And in my head, that just looks really messy. And I've made the mistake before where I just kind of I just don't see one of these numbers somehow. And you just don't really recognize how easy it is to make these mistakes until you have this huge calculation that you need to do. So I find just by organizing it, I'm far less likely to make one of those mistakes where I leave a number out. And again, that's the kind of mistake which is going to significantly change your answer. If you leave out an 8, that's basically the same as leaving out a 10. So just make sure that that you're doing everything you can to not make one of these mistakes. So that's what the organized steps here. So we get 8 times 4 times 9, 3 times 6 times 5 in the denominator. So how I like to do these is just make the maths easy. So this is what I was talking about before. It's not going to matter if we change one of these numbers a little bit. It's not going to get us from 100 to 1,000 or something like that, which is usually how far the answers are apart. So if I'm looking at this, so my golden rule is make the maths easy. And by easy, I mean if I ask you that question, you will immediately know the answer. So without even thinking, you just know the answer. So 2 times 2, 4, that's easy. But if I said something like 7 times 8, you probably have to think about it. And in those instances, I just make it easy. So I'll show you what I mean by that. So when I'm looking at these equations, so I'm looking at this numerator here, I like to just look for things which are easy. Now, I'm spotting this 9 here, and I'm thinking that would be really easy if that was a 10. 10 works with anything. So I'm just going to change that 9 to a 10, and then maybe I'll multiply this by the 8. So that gives me 80. 80 times 4, a little bit difficult. 80 times 5 would probably be a little bit easier for me, and that would give me 400. Now in the denominator, we just do the same thing. So my eyes immediately go to this 5 and 6. So I think 5 times 6, 5 times 6 is 30, and times 3, that's easy enough. 30 times 3, that's 90. Okay, so this is going to be different for everyone, but I would just say, ask yourself, do I immediately know that answer or not? And if you don't, just make it easy. Okay, so now that we've got this, everything's still exactly the same. Now 400 divided by 90, not easy. So we just change this to 100. That's so easy. So 400 divided by 100 is 4. So this final answer would be 4 times 10 to the negative 6. So I've gone from this very crazy looking sum of numbers to an answer, and you can probably do that in about a minute once you've practiced this a little bit. Now, I get quite a lot of pushback about this making the maths easy and really changing these numbers. But I'll show you, hopefully, try to convince you that it's not an issue. So 90% of the time, I think you're going to be absolutely fine, and your options are going to be so far apart that it's not even going to matter that you make a little estimation, because your answer is going to be, let's say even you say you got the answer 20 or 30 or something like that, and it should be 10. So if you did everything correctly, the answer would be A. Which answer are you going to pick? If you got 20 or 30, there's no way you're not picking A anyway. So 90% of the time that happens. 9.9% of the time, what happens is you're stuck in between two answers. So let's just say you had 8 divided by 6, or we'll say 80 divided by 6 or something like that. So not the nicest, and your answer, I'll actually just calculate what this is exactly. Okay, so I've just made two answer options. One of them is correct, and one of them is going to be another answer that we need to decide between. So I'm looking at this thing, I've got 80 divided by 6, and I'm thinking, oh, that's a bit hard. And I think when people do this, they kind of often gravitate to the things like 5 and 10, which is fine. But you can also pick more irregular numbers that actually make it really easy for you. So you could go to 5, for example, that would be fine. But 80 divided by 5, that's still a little bit tricky, I think. So an easy number, I think, would be changing this to an 8. You know, it's closer. 10 would also be very easy, but 8's closer, and it's kind of equally easy. So don't just go to a 10. Actually think about what's the closest number, which just makes this an easy solve. So 80 divided by 8 is just going to equal 10. Now, this is what I'm saying happens 10% of the time, nearly 10% of the time, is that you've done some estimation and you've ended up with an answer which is 10. Now, I am 3.3 away from this one, and I'm 3.3 away from this one as well. So how do I pick which answer I choose? Well, I need to just see that what I've done is I've changed a 6 to an 8, so I've increased my denominator. Now, what I like to do is just see the effect of doing that change. And how I do that is I just set up a little experiment like this. So something that I know is true. So 1 divided by 1 is 1. Now, what happens if I increase this denominator? So let's say I changed it from 1 divided by 1 to 1 divided by 2. Well, that means my answer isn't going to be 1 anymore. It's going to be 1 over 2. It's going to be a half. So my answer has gone down. So the relationship between increasing the denominator and my answer is that if I increase the denominator, my answer will go down. So this is called an inverse relationship. Conversely, if I get rid of all that, let's say I decreased my numerator. Actually, I won't do that. It's going to get a little bit annoying for me. Let's say I increase my numerator, change this to a 2. It's now 2 divided by 1, which is 2. So I can see that if I increase my numerator, I increase my answer. Now, you do enough of these, you just kind of learn it. But this is a good example of how you can just verify things for yourself. So what I've done is I've increased my denominator, so I know that this is actually an underestimate. Okay, because I found out before that if the denominator went one direction, the answer went the other direction. So all I need to know is that this is an underestimate, so therefore the correct answer is B. So hopefully that's convinced you that it's still okay to do these roundings. It makes things far easier, which I actually think leads to less mistakes. So even though you're losing some accuracy, you're less likely to make a significant mistake that will draw you to the wrong answer. And 99.9% of the time, it's going to be very easy to troubleshoot. Now, admittedly, I'm running out of space. Admittedly, there is 0.01% of the time. This isn't fact check, but around that percent of the time where you're just going to have to redo. You're just going to have to redo your maths. So go through, change all of the numbers, change the things that you've estimated. Really doesn't happen very often, but if it does, it just means you've got to redo your maths and it might take you an extra minute to solve. Now, I just wanted to finish with another circumstance which comes up a little bit, and that's if we had a very small numerator. So the numerator is the top number, denominator is the bottom number. But let's say instead of 400 divided by 100, now that's easy. The reason that's easy is because the numerator is bigger. If we had a situation like 1 divided by 400, and we'll just say that, we'll just actually say 1 by 400. That's quite hard to solve. And it's because the denominator is bigger than the numerator. So we can solve that by making the numerator bigger. Okay. Now we can't make it bigger, but we can make it kind of look bigger if we represent it in scientific notation. So what I mean by that is if we go back up to index laws, you might have forgotten this one, but a to the 0, so anything to the power of 0 is just 1. And if we multiply anything by 1, it's just itself. Okay. So what we could do here is we could actually rewrite this as 1 times 10 to the 0 over 400 by 10 to the 0. Okay. So all I've done here is I've just written out a 10 to the 0 here, which is just the same as 1. So on the top, it's just 1 times 1 and 400 times 1. So I haven't changed anything. But the reason is because then I can manipulate these numbers in scientific notation. Now, I kind of spoke before about how really in scientific notation, as all we're doing is representing numbers in a different form, we can kind of have them in the tens pile or we can have them with the number. Okay, so that's why this is important here, because what we could actually do is I like to think of it as we can kind of steal one of these tens and give it to that number. So for example, we have 1 times 10 to the 0, which we just said equals 1, yeah? But we could also represent this as 10 times 10 to the minus 1. And if we solved this, if we work this out, we put our decimal point in and we have a -1, so we'd actually jump this one spot. So that just equals 1 again. So this also equals 1. 10 times 10 to the -1 also equals 1. So what we could do is we can just keep jumping until this numerator number becomes greater than the denominator. So for example, we could go, what I kind of want is I want 1,000. So I can say 1, 1, 2, 3. So I need to do 3 jumps to get to 1,000. 1,000 times 10 to the -3 over 400 times 10 to the 0. Okay, so now you can see that my numerator is bigger than my denominator. This I think is still not easy enough. I would just say 500. So I'd say 2 times 10 to the, that's -3 minus 0, so that just stays as -3. Okay, so it feels really odd, but I promise you this makes any of these sums where you've got a really small numerator and a large denominator, it makes it really, really easy. And it's just, again, it's just about preventing mistakes. So give this a go. I know it feels a little bit weird, but I promise it just makes all the maths a lot easier. And my last little note on index laws is just, if you're doing anything in index laws, make sure all the numbers have both a number and an index. So for example, if we had 10 divided by 5 times 10 to the 2 or something like that, I've made this mistake before where I've just gone in autopilot and I've said, okay, 10 divided by 5, actually, I'll do a different example. I'll do 5 divided by 5 by 10 to the 2. So I've just thought, okay, I've got the same thing on the top and the bottom, so we can just cancel those out, and my answer is 10 to the 2. Now that seems reasonable, doesn't it? I've just cancelled that number off, and just whatever's left is my answer. Seems reasonable, but I'll show you why it's not the case. So if we had represented both numbers in scientific notation, this one would become 5 times 10 to the 0, because 10 to the 0 is just 1, divided by 5 by 10 to the 2. Now you can see here that these 5s can still cancel off, you can still do that, be my guess, nothing wrong with that, but now you see that we have 0 minus 2, so this answer will actually be 10 to the -2, 1 times 10 to the -2. So if you think about that, this is a really bad mistake to make. We've gone from saying that the answer is 10 to the 2 to all the numbers have both a number and an index. So for example, if we had 10 divided by 5 times 10 to the 2 or something like that, I've made this mistake before where I've just gone in autopilot and I've said, okay, 10 divided by 5, actually, I'll do a different example actually. I'll do 5 divided by 5 by 10 to the 2. So I've just thought, okay, I've got the same thing on the top and the bottom, so we can just cancel those out, and my answer is 10 to the 2. Now that seems reasonable, doesn't it? I've just cancelled that number off, and just whatever's left is my answer. Seems reasonable, but I'll show you why it's not the case. So if we had represented both numbers in scientific notation, this one would become 5 times 10 to the 0, because 10 to the 0 is just 1, divided by 5 by 10 to the 2. Now you can see here that these 5s can still cancel off, you can still do that, be my guest, nothing wrong with that, but now you see that we have 0 minus 2, so this answer will actually be 10 to the negative 2, 1 times 10 to the negative 2. So if you think about that, this is a really bad mistake to make. We've gone from saying that the answer is 10 to the 2 to 10 to the negative 2. So our answer is now 10 to the power of 4 away from each other. We're definitely going to get the wrong answer. And ASA recognizes these mistakes. They know when these mistakes happen, and they know the circumstances that they can provide, the environment they can provide to make you make one of these errors. So, and I guarantee if they think that a mistake will happen, they're going to put that answer in the answer options so that you'll pick it. Because if you think about it, if you made this mistake and you ended up with a huge answer different to all the options, you're going to say, oh, okay, I must have made a mistake, and you're going to redo it. So what they do is they go through and they find the mistakes that people are going to make, predict them, and then put those answer options in. So just make sure you're aware of that, and just do everything you can to prevent these mistakes happening. And just to kind of go through the rules that I think help that, there's making sure that if you're doing anything in scientific notation and index laws, make sure both numbers or all the numbers are represented that way. Making the maths easy helps, and making sure the numerator is bigger than the denominator, using that method that I showed you before. And then when you're going through that process, just make sure you do SOS, scientific notation, organize, solve. So one of the most common traps that I see is, for example, on a graph question, and it says, what's the value of this at this? And they give you some value here, and you go up and you get this value, and then you pick that answer and you get it wrong, and you think, why did I get it wrong? And what you didn't notice is that the units on this graph are different to the units in the question. So if that's the case, you need to have a process to be able to convert those units, and that's what we're doing today. So a few people kind of try to wing this because, for example, the question might be saying, what's 60 kilometers per hour in meters per second? And in some of these cases, people can do it, so they kind of think they can do anything. But the whole point of the GAMSAT is they give you a really unfamiliar situation and takes you out of your comfort zone, and then you can't do it. So we really need to have a robust process so that we can convert any unit, and that's what we're going to do today. So we're going to rely on a few kind of mathematical principles here to get us there. So the first thing is that we can multiply by 1 and not change the value. Okay, so if I had, so that's multiply by 1. So just to give you an example of that, if I had 5, I could multiply that by 1. It's still five. I could also multiply this by 10 over 10. So the first thing is that we can multiply by 1 and not put zone, and then you can't do it. So we really need a situation. In these cases, people can do it, so they kind of think they can do anything, but they're different to the units in the question. So if that's the case, you need to have a process to be able to convert those units, and that's what we're doing today. So a few people kind of try to wing this because, for example, the question might be saying, what's 60 kilometers per hour in meters per second? And in some of these cases, people can do it, so they kind of think they can do anything. But the whole point of the GAMSAT is they give you a really unfamiliar situation and takes you out of your comfort zone, and then you can't do it. So we really need to have a robust process so that we can convert any unit, and that's what we're going to do today. So we're going to rely on a few kind of mathematical principles here to get us there. So the first thing is that we can multiply by 1 and not change the value. Okay, so if I had, so that's multiply by 1. So just to give you an example of that, if I had 5, I could multiply that by 1. It's still 5. I could also multiply this by 10 over 10, and this will equal, if we think about our fraction multiplying, this will end up being 50 over 10, right? But that's still 5, and that's because 10 over 10, the top is the same as the bottom, so that's the same as multiplying by 1. Okay, so we can multiply anything by 1 as many times as we want, and we're not changing the value. Okay, the second rule is that if we have the same thing in the numerator and the denominator, they will cancel out. Okay, so what I mean by that is if we had, if we had 5 over 2 times 2 over 3, right, we've got the same number in the numerator and the denominator, and they will cancel out, okay? Because if you think about it, we're doing 5 times 2 divided by 2. So they're opposite. That's kind of like the algebraic manipulation stuff that we were doing. So if we have the same thing in the numerator and the denominator, we can actually just cancel these things out. Okay, so these are the two kind of foundational rules that we need to follow to convert our units. So I've just written that out a little bit more clearly, so we can multiply by 1, and that's fine. And if we have the same number in the numerator and the denominator, we can cancel that number out. And just to restate, what we want to do is we want to convert 60 kilometers per hour into meters per second. So how I want you to go about this process is write them like this. So 60 over 1 times by kilometers per hour. What we really want to be doing is separating the numbers from the units. And we know that any number over 1 is just itself, so that's 60, and we're just multiplying that by kilometers over hours. So this is the same as kilometers per hour. Now, if we think about the second rule, we want to cancel the kilometers and the hours, right? So what we could do here is we could, let's just say I had a magic wand. I could just multiply this by hours in the numerator, and then these two hours would cancel. And that's good because we don't want hours, we want seconds. But it's quite clear that I can't just do this. I can't just cancel a unit because if I did, I've gone from 60 kilometers per hour into 60 kilometers. They're clearly not the same thing. So what I could do, if we think about the second rule, is I could have the same thing in the numerator and the denominator, and now that is good because I've not changed the value, but it's kind of pointless because I've just cancelled an hours, but introduced another one. However, we can let, it's the same, as long as it's the same in the numerator and the denominator, we can actually put any value in there. So we can actually put down here 60 minutes. And if you think about that, 60 minutes is 1 hour. So what we've done here is we've cancelled the hours unit and we've introduced a minute, which is perfect. And if we keep going with that, we can then keep cancelling the units. So when you're doing this unit conversion process, just ignore all the numbers and only do the units. So my process is kind of identify the unit that you want to cancel, put the same thing on the other side of the fraction, then put the unit that you want to go into on the other side of that, and then balance it out with some number. So if we do that process for minutes here, we want to cancel the minutes. So let's put it on the other side of the fraction. Then we want to put the unit that we want to go into on the other side of that. And then we just need to put a number on either the numerator or the denominator to make this balance. So what I do here is I'd say, well, there are 60 seconds in 1 minute. So if I put a 60 down here, that's going to balance out. And the effect of that is we can then cancel this minutes off. And you can see that now we've basically just said that we divide by 60 to convert from hours to minutes and divide by 60 again to go from minutes to seconds. And hopefully that just makes a bit of conceptual sense if you think about that. So if you look at the net effect of that, we've now gone from hours into seconds, and we can do the same thing for our kilometers. So we can times by, we've got kilometers in the numerator, so we go down here and we put it in the denominator. So they will cancel out. Then go up here, put the unit that we want, meters, and then we need to balance that out. So there are 1,000 meters per kilometer, and then the effect of that is we cancel off the kilometers. And now the only units that we have left, if you look, are meters per second. That was a horrible color choice, but they're the only units that we have left in our equation. And the beauty of this is now we just do our scientific notation index laws kind of process, and we can solve this really, really easily. So because it's really messy, I like to just rewrite it. Now, when I'm rewriting things, I like to put all the numbers together. Oops, sorry. And all the units over here. Now, the reason I do that is if you look at how I've written that S, if that was here, you could very easily interpret that as a 5, and I'm almost certain that I've done that. So I just like putting the units somewhere else so that I don't make a mistake. And now that we've got this written out all nice, I've got all my units there, we can actually see that we can just cancel out these 60s because we've got the same thing in the numerator and denominator, and then it's just scientific notation. So this is, I'm going to go to 10 times 10 to the 2 because I want the numerator to be bigger, and then I can just say this is the same as 6 times 10 to the 1, and I'm just going to make that a 5 to make the maths easy. So then 10 divided by 5 is 2, 10 to the 2 divided by 10 to the 1 is 10 to the 1, so that just equals 20 meters per second. So we've just gone from 60 kilometers per hour into meters per second, and really you can start to see that that's why this index law process is really helpful, because you can do a bunch of different things, and then once you have all the numbers, you just solve it really easily like that.
Okay. That was a lot, but that was a lot. That was a lot. Okay, I will do now some of the GAMSAT questions for the next hour or so. Okay, we're going to do questions 44 to 48 to start off with in the pink practice test A. Let me just turn on the fan because it's hot and I'm tired. Maybe we do like a quick little cognitive rest reset. I'm gonna do that. If you'd like to join in. a little cognitive reset, I think. Just have a little break. Brain's fried from all that maths. So what the cognitive reset is, it's focusing from the place of emptiness. So where there are no thoughts, or there's no strong activity, and it gives you just a chance to reset, basically. I'll do that for 5 minutes or so. It's really good for like academic study and learning. Cool. Now we have all our energy coming from that empty place. Limitless focus. That's what it is. It's very cool. Okay. Questions 44 to 48. See if any of that math helped us out. Probably do about half an hour about half an hour more, and then we'll call it a session. So I need a snack. I need to go for a walk and go to work. So I'm just going to start by defining the question. So consider two genes on the same chromosome, each with two alleles, AA and BB. One octad has the following order: AB, 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 AB. Which of the following could be the genotype of the diploid myocyte? Okay. Okay, diploid myocyte. So A, A, B, A, B, 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 A, B, B equals which of the following could be the genotype of the diploid myocytes equals so I want to get to A, B, A, B, A, B. So AB times 4, AB times 3. Okay, so I'm gonna need the STEM information. So the information I'm looking for is what the fuck is an octad? What is an octad? So an octad contains the genes, the alleles actually. An octad contains the alleles. No, I don't know. Okay, I got the octad, tetrad, myocytes. Do not consider recombination for question 40. Okay. Diploid myocyte. So diploid myocyte. Okay, so many fungi reproduce sexually by forming diploid cells known as myocytes. Okay, which undergo meiosis to form haploid spores. Some species, the spores resulting from a single myocyte are contained in a sac known as the ascus. It's spores resulting from a single myocyte are contained in a sac known as the ascus. Okay, so the ascus is that octady thing. Ascus. If you want to represent sporulation in one such species for just one of its 7 pairs of homologous chromosomes, for just one of its 7 pairs of homologous chromosomes. A total of 8 haploid spores are formed. Four haploid pre-spores formed during meiosis. Each spore then undergoes a single mitotic division to produce 4 pairs of haploid spores, an octad. What represents spore relation in one such species for one of its 7 pairs of homologous chromosomes? Okay, so one of its 7 pairs. Okay, so that's what that is. So that's what AB is. Okay. Sporulation in one such species, 7 pairs of homologous chromosomes. Okay. A total of 8 haploid spores are formed. 4 haploid. Okay. Okay. Shows the one possible order resulting from the haploid. Shows only one possible order resulting from the diploid myocyte genotype, AA. Okay. Let's go to the final position in the ascus. The 2 pre-spores. Okay, we're getting somewhere. With respect to the final position as an ascus, 2 spores formed in the mitochondria could be reversed as shown by the curved arrows. The same is true for each pair of pre-spores in the second mitotic division. The products of each mitotic division are located next to each other as pairs. Okay, so if I have AB, so genotype of the diploid myocyte, so it'd have to be have to be lost. Okay, let's start again. Let's start again. Consider two genes on the same chromosome, each with two alleles. Chromosome, I get confused. Chromosome, allele, gene. So a gene has the allele, sorry, the alleles on the gene and then the gene and then the alleles are in the chromosome? No? So that is two genes, so times two genes on the same chromosome, each with two alleles, AA and BB. So gene, so gene 1 equals AA B B, gene 2 equals AA B B. One octet has the following order. Which of the following could be the genotype of the diploid myocyte? Okay, diploid myocyte. Where is that? Many fungi produce sexually by forming a diploid cells known as myocytes. Yeah, diploid myocytes, which undergo meiosis from haploid spores. Sporulation in one such species for just one of its 7 pairs of homologous chromosomes. Total of 8 haploid spores are formed, 4 haploid pre-spores, 4 haploid pre-spores, a tetrad are formed during meiosis. Each pre-spore then undergoes a single mitotic division to produce 4 pairs of haploid spores, an octet. Can I just do a Punnett square, whatever the fuck they're called? Can I go A? Oh, I'm just baffled. I'm just baffled by this question. We stick it out though. We stick it out. I just don't know. How can I change my approach here? What can I do? What can I do here to change my approach? Let's try and define the question a bit more here. Consider two genes on the same chromosome, each with two alleles, AA and BB. One octet has the following order, blah blah blah. Which of the following could be the genotype of the diploid myocyte? Okay, what is the diploid myocyte? Diploid myocyte. What is that? Where is that? Figure 1 represents sporulation in one such species. Just fungi, many fungi reproduce asexually by forming diploid cells, known as myocytes. Is that? Okay. Okay. Okay, okay, okay. Okay, okay, okay. 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 So, I have A, B, My goodness, this is hard. Yeah, I just really don't know where to go with this question. It's crazy. I've spent like 25 minutes on it, 20 minutes on it. I just don't know what to do. I guess we go back to trying to find the question again somehow. Consider two genes on the same chromosome. Okay, two genes, same chromosome, each with two alleles, AA and PP. One octet has the following order. I'm debating whether I go get the answer, or if I just sit with not knowing this and try to figure it out still. Like, feels like a colossal waste of time just sitting here, but I think there's something to it. I think there's something to like me figuring it out myself, if that's possible. Maybe I go to the next question and see what that says. A diploid myocyte is heterozygous for a gene A. Consider the possible A in the assay that are listed below. I don't think that's going to help going to the next question. Hey, I'm going to leave this set and come back to it maybe tomorrow. I'm just going to do question 47 and 48. Oh, they're the same set basically. I'll do question 49. Which of the following is closest to the ratio of the concentrations of the compound in each solvent? Which of the following is the closest to the ratio of the concentrations of the compound in each solvent? Okay. So, looking for ratio of concentration for a compound in a solvent. Ratio R of C ratio of concentration for compound solvent. I don't know what half those words mean, but that's okay. Ratio of concentration for compound in solvent. So the diagram below shows the partitioning of a particular compound in equal volumes. So the compound is equal, so let's make that 1. Let's make that 10 actually. Compound in equal volumes of 3 mutually immiscible solvents. That means 3 mutually solvents. Mutually immiscible. So the compound, so there's times 10 of the compound in solvents. The total amount of the compound dissolved in the system is 2.3 mole. Dissolved in the system is 2.3 mole. Okay, so total 2.3 mole of compound. Okay. The amount of the compound dissolved in solvent is in solvent 2 is 1.2 mole. Okay. So I can go 1 plus 3 plus no, A plus B plus 1.2 equals 2.3. 2.3. Okay. The amount of compound dissolved 2.3. So together A and B equal, I don't know if this is mu, but 1.1. Okay, which of the following is considered a ratio? Okay, so I want the ratio of the concentration of the compound in each solvent. Okay, the ratio. So the ratio of 1 to 3. So 1 to 3 is 1540. So that can be 3 or 8. 3 over 8. So 3. 12. 2 to 1. So 2 solvent 2. So solvent 2 is 1.2 mole. I see. 1.2 mole. And the ratio is 3 to 8 with 1 point, what's the total? 1.1 mole. Okay, so what's 3 over 8? 1.1. So what goes into 1.1? 0.1. So what is it? So it's like, so it's 3 mole, 2.3 mole, 1, and 3 equals the ratio between 0.3 so let's say it's like 4 to 1, 4 for 2, 2.9 to like 2 2 C C12. So one is 12. Concentration. I have no idea. No idea. No idea. No idea. Okay, I'm pooped and I could be bothered anymore. Like over, like 40 minutes on two questions with no answers is very demoralizing. But we continue forward. Okay, okay, so we'll call it there for a day. Um, not a very uh, what am I trying to say? Not a very enjoyable session this morning, but we're bound to have those, and it's how we rebound from those that that matters. So we continue forward at 8 a.m. tomorrow morning, and we keep moving, ladies and gentlemen. We keep moving. So I will catch you all in the next one. Happy studying.